And where we left off, well, first, are there any questions? There have been great questions up till now, but I didn't have the recorder going. Somewhere in here I have my lab. There it is. Okay. Is everybody here, was here last time and got a copy of the lab, right? Yeah, okay. Now, if my memory's right, which it sometimes isn't, sorry, we're in the lab. Y'all, of course, had read page 359. We talked a little bit about it. We did part A, which is celestial pole and equator. That was 360 and 361, 362, and the top of 363. Then page 363 started celestial coordinates. We did that. Part C was celestial, the star finder. We did that. And we were on part D and close to finished. And remind me, did we do number 11 at the bottom of page 365? We did do that. And we did 12 also, right? Okay. All right. And we had filled out the three tables. Table 47. Okay. Some of the things are a little, 47, 1, 2, and 3. Right? But we didn't start 13 yet, did we? All right. So here we go. Any questions before we get started?
Yeah, I didn't do, I missed March 21st. Second of sun.
Okay, on the table?
On the table, which one was it?
Okay, it's not, remember that SEC should be DEC. On all three of those tables. I don't know how they got that. Okay. And what's the question?
I didn't get it.
I'm sorry?
I missed March 21st.
Of which one? Was it March 21st on all three tables?
The first one.
The first one, okay. When at our latitude, okay. Now, you got March 21st declination of the sun for the other two.
Right.
Okay. What does declination of the sun mean?
Descending.
Second?
Descending.
Okay.
Descending.
Now, declination, what that means is where it is relative to the celestial equator.
Okay.
Okay? Now, no matter what time of year, no matter what anything, the declination of the sun on the same day in subsequent years is always the same elevation from the sun. So therefore, the declination of the sun, how far above or below the celestial equator is the same. So if you got it for table 47.2 and 47.3, aren't they the same? Same for 47.1. Doesn't matter where you are, what the declination of the sun is. It's the time of year. Let me see. This is not the right class. Okay, here's the right class. Kyria is here. And Donald, right? All right. Anyone else come in, Sister Caldwell? Okay. Now, any other questions on what we've done so far? Everybody up to snuff here? All right. Then we were on page 366 of the lab, next to the last page, and it says, Eratosthenes, who lived in the 2nd century BC, before Christ, was a Renaissance man before his time. He was an astronomer. He was a geographer. He was a historian. He was a mathematician. And he was a poet. Well, by the way, that reminds me, did I read these two announcements to you? Yes. Yeah, I did, about the career day, college career day. Okay. I want to make sure y'all heard that. All right. When I read the poet, one of those was about a science group called the Poet. Okay. Now, with such a diverse background, it is not surprising that he was the director of the Great Library of Alexandria. Now, do y'all know where Alexandria is or what we're talking about there? Alexandria is a place. Okay, not the female name, but. What were some of the earliest civilizations that we know about? Name a few. I can't hear. Egypt. You certainly are right. And that's the one where Alexandria is. Okay? Alexandria was a city, is still a city, in the very northern part of Egypt, right on the Mediterranean. It was, Egypt being one of the most ancient civilizations, it had a jump on a lot of the others in education and stuff, and they developed a world-class library there. So when they're talking about the Great Library of Alexandria, they mean it. A great library of Alexandria.
It was an Egyptian library, but it was in Alexandria.
So it was
an Egyptian library, but it was in Alexandria territory.
Well, Alexandria is a city in Egypt.
Okay.
Yeah. So in fact, it may have been the capital at that time. I don't think Cairo was even. In fact, they may have even called it Egypt at the time. But anyway, that was a major city and the major library in the world, the Great Library of Alexandria. Now, it also has a little bit of a history. And since we're talking about it here, that could be a paper topic if someone wanted to look into it. Unfortunately, this is, to me, a really sad situation. Of course, centuries after this is talking about, millennia after this is talking about, Europe now has become the center of civilization. And generally for the Christian part. Europe was still pretty backwards academically, okay? And by this time, a millennia or so later, Islam had pretty much taken over Egypt, okay? Not completely, it still hasn't, but it was the thing. And during there were four major ones of these. Anyone know what I'm talking about? Conflicts between Christianity and Islam. The four great crusades. Okay? One of these crusades, sadly enough, they got as far as Egypt. And unfortunately, most of the soldiers, the people actually doing the fighting, were basically illiterate serfs. You know, their honchos rounded them up and said, you have to go fight. In fact, if you look at it, most wars have been fought not by the people who caused the wars, but by people who had no choice. Okay? This was one of those kinds. And they knew these were mostly Muslims that were in this great library. So all this stuff in there, which they couldn't read or understand what it was talking about, must be pagan stuff. So they burned most of the archives in this great library of Alexandria. So sad. I mean, if it hadn't been for the fact that scholars had come from around the world to gather at Alexandria and then had copied things and taken them back to their libraries, most of civilization would have been lost. Okay, but this has been spread throughout the rest of the known world. I'm not talking about China. They weren't communicating yet. You know, they didn't even know each other existed. But yeah. But anyway, so that was a terrible aside. Okay, so the Great Library of Alexandria. In one of the scrolls at the library, Eratosthenes read that at noon on the 21st of June, at the southern frontier outpost of Syene, Egypt. Now, they don't list that on here. The very southern outpost of Syene, Egypt. Not listed here. However, it does say near the first cataract of the Nile. Okay? Now, I'm not absolutely certain what a cataract is. I think it's one of the, like a small waterfall or something like that. In other words, where it starts happening. Now, my guess, that's probably not too far from where the S1 dam was built. That was built during my lifetime, probably not through many of yours, but Egypt built this to create electricity, hydroelectric plant. The Nile River is a really big, powerful river. You don't build dams on flat land, you build it up where there would be things like waterfalls. So I'm guessing, just because I can find the S1 dam here, it was probably pretty close to that. The first cataract of the Nile, it said. And it says at that location, obelisk cast no shadows. At noon on the 21st of June, southern frontier outpost in Syene, Egypt. Okay? Obelisk cast no shadows. As noon approached, the shadows of the temple columns grew shorter and shorter until at noon those shadows disappeared. Reportedly, a reflection of the sun could then be seen at the bottom of a well. You know, just a real deep well. You could look in there and see the sun directly overhead. Okay? On June 21st, at Syene, the sun was directly overhead. That's what I just said. And we don't have a celestial globe, but you tell me what you think the latitude of Syene was. I'm going to point you okay, here we go. Probably the best figure to look at to determine that is at the bottom of page 361. Okay? Someone tell me what the ecliptic is. It's what?
The path turns circle and it's called the ecliptic.
Dotted circle.
It's what?
It is the winter circle.
Dotted circle.
Yeah, the dotted circle, the eclipse. What is the eclipse?
The sun goes around.
Okay, that shows where the sun is any time of the year. It's on the ecliptic, because that eclipses the sun. Okay? Now, if the sun is right there, looking at this figure, what would you guess the latitude of Syene, Egypt to be? Say again? Bottom of page 361. That diagram there. June 21st. Does that ring a bell? Summer solstice. Where is the sun on the summer solstice? Anytime it's at the ecliptic. Well, on the summer solstice, say again? Absolutely, and therefore that would be the latitude of the ecliptic. Okay? But of Syene, Egypt, because that would be where the sun would be. Right over it. So let's see what it says. To determine the latitude of Syene. So 23 and a half degrees, 23 degrees, 30 minutes, however you want to write it. North. Okay? Because Syene, Egypt is north of the equator. And sure enough, now I don't know if we mentioned this before. I think it says coming up in the next chapter. Does anyone happen to know, and if you look on the globe here, the S1 dam is right above this dotted line here at 23 and a half degrees north. Does anyone know what that dotted line stands for? A little louder? No, okay, no, that's not the, it's a different dotted line from the ecliptic, okay? This is at 23 and a half degrees north, all the way around at 23 and a half degrees north. It's a dotted line. There's another one at the dotted line south of the equator.
That's a tropic.
The tropics, exactly. The northern one is called the Tropic of Capricorn, I think. And the southern one is the Tropic of, no, you're right. Northern is Tropic of Cancer, southern one is the Tropic of Capricorn. Yeah.
Because the Cancer constellation can be seen from the moon.
Say that
They
again.
name it because the constellation is Cancer constellation.
I'm trying to remember. Does someone know this constellation better than me? Is there a constellation called Cancer?
Yeah.
Okay. I know there are all sorts of weird ones. In Capricorn, I know there is. Okay. So, yeah. So it must be there at those extremes. Okay. Now, in between those two tropics, we call that the tropics. Okay. Tropical weather, tropical countries. Colombia, Ecuador, Venezuela, they're all in the tropics. Okay. Costa Rica, all the countries that are in between there are tropical countries. We'll talk about that more in a later chapter too. There are two other dotted circles on the globes, one down here and one up here. Anyone know what those are? Dotted circles that go around. The one way up north is called the Arctic Circle, and the one down south is the Antarctic Circle. Guess how far those are from the poles? How many degrees? 23.5 degrees from the poles. Okay, and those represent, if you're north of that Arctic Circle, there will be at least one day of the year when the sun doesn't come up, and one day of the year when it doesn't set. Same thing with inside, beyond the the Antarctic Circle. Okay. We'll talk about those at a later time too. Okay, in fact, this next chapter we didn't. Sorry, that took longer than I thought I intended. But everybody got that one then, all right?
Yes.
Okay. Number 14. It says, readjust your celestial globe, we don't have one, for your latitude. What range of declinations can stars have so that they never set, that is, they're always above the horizon? So I don't have a circle, but I can do our handy-dandy little drawing here. Okay? Here is the globe. Here we are standing here in Birmingham or Bessemer, Alabama. Okay? And if my memory is correct, I ought to go and get it now anyway. Oh, that will stick so easily. Okay. Here's a map of Alabama we'll be using in a couple of the labs. Bessemer, Alabama here. 33 degrees, 23 minutes, 45 seconds. That's our latitude, north. Okay? So that's what we're going to be basing this on. That says our latitude. Okay? So that's going to be 33 degrees, 23 minutes, 45 seconds, approximately. Okay? There's our horizon, and there's the celestial sphere, our hemisphere, actually. Okay? Now, directly above us is our, what's that point called on the celestial sphere? Our zenith, exactly. Then the celestial equator would be that same measure, 33 degrees, 23 minutes, and 45 seconds from the, what would this line be? Celestial equator, because that's the equator down here. Here's the celestial equator here. Okay. Now, what would be this line here? What would that represent? North Star or Polaris. North Star or Polaris, so I'll put me a star there. And that happens to be what angle above the northern horizon? We did this the very first question on this lab, almost. What would that be? 33 degrees, 23 minutes, 45 seconds. Because remember, that angle, this is above the northern horizon, is exactly what your latitude is. Here's our latitude, that's that, that's this. These are all the same angles. Remember we did that? Where's alpha? Okay, no. What is alpha? Okay. Now, at nighttime, you see the North Star over here, the sun somewhere else, the other side is down here somewhere, okay? Now, it's asking for what stars never set. Can anyone name one star that never sets? Polaris, of course. It's going to be sitting right there all night long. It's never going to change. Now, all the other stars go around it, right? Now, that means that every star that is close to the North Star is going to go around in a little circle. They'll never set. And then those a little bit further will do, they'll all the way up until this far down. Those stars will never set, right? They'll get real close to the horizon, but won't set. Anything beyond that, those are going to set, okay? Does that make sense? These that are over here, those are going to set big time, okay? Now, what we need to know is the range of declinations that stars can have so they are all never set, that is, they are always above the horizon. Well, the declination is what? Y'all answered this earlier. Yes, how many degrees you are above the celestial equator. So, the stars that never set are those, certainly that are here, but then if you rotate those around, there's another 33, 23, 45 to here, okay? And then what we have to do is figure out what the range of declinations are from here to there. We know this is 90 degrees. North Polaris is 90 degrees from the celestial equator, so it's going to be something to 90. And by the way, if I'm not mistaken, I did see Brenda's come in, right? Yeah. I forgot to mark you, I think. So let me make sure I marked you. And then Shikaya, right? Yeah. Okay. If you hadn't come in, I would have forgotten. Okay. So anyone else who I missed coming in? Because I get the yakking and I don't pay attention. Okay. So what we need to do is basically double this and then figure out what angle that is. That would be the declination of the stars from here to 90 degrees. That would be the declination of those that never set. So let's see if we can figure that out. Okay? This declination of the North Star is 90 degrees, right? Let's call that 89 degrees. Anyone have an idea? 59 minutes and 60 seconds, right? Because 60 seconds make 1 minute. That would make it 60 minutes, and 60 minutes is 1 degree. That would make it 90. So that just makes the subtraction easier, okay? Now, so we're going to 90, so let's subtract our 33 degrees, 23 minutes, 45 seconds from that, and that would be this declination here. What would that be? Pretty easy to subtract this way too, isn't it? 56 degrees, 36 minutes, 15 seconds. So from 56, 36, 15 to 90 degrees, that would be the range of declinations of the stars that never set from where we live. Okay? You see why that's true? Do you see how we did it, huh? Oh, okay. My first question was, what's the angle between the celestial equator and the North Star? 90 degrees, because the globe, the North Pole is 90 degrees from the equator, right? So it's 90 degrees. I want to subtract this number from 90 degrees, but that'd be hard. So what I do is write 90 degrees as 89 degrees, 59 minutes, and 60 seconds. So 60 seconds makes one more minute, and that makes this 60 minutes. 60 minutes is 1 degree, so that makes that 90 degrees. So writing it this way just makes the subtraction so much easier. Okay? And I'm lazy, so I do things the easy way. Okay? Sorry about that. I know y'all are hard workers, and you probably don't want this laziness. Okay? So, that's the range of declinations. Now, the next few questions here relate to two planets. Okay? One, I'm pretty sure I've never seen. Certainly, if I've seen it, I didn't know what I was looking at. Okay? Because it's so stinking hard to see. The other one, though, is possible. Okay? In fact, I see it all the time. But I'm not sure I would have answered this question. Now, I don't have the current data, so I'm going to use the data that I got from Birmingham Southern several years ago, and we'll just pretend it's about like it is now. Okay? Now, they gave on here some of the planets and when you can see them. Now, we're closest to November, so let's deal with November. Mercury is visible, they say, in late November, so we'll just assume that's now, in the early morning sky. So our question here is, when is Mercury visible in a dark sky? Just before sunrise. Agreed? Okay. Now, why is Mercury just before sunrise? Why do you think that would be the case?
Because the sun blocks it out.
Second?
The sun blocks it out.
Okay. Yeah, you're right on the money there. Okay. Tarsha, were you going? Yes.
It's the same direction as
Yes, exactly. Tarsha, you want to be the sun again? You seem really bright today. Okay. So Tarsha is going to be the sun. Okay, and we're over here. Somewhere in between us and the sun is Venus, right? And somewhere closer to the sun is Mercury. So we'll never see Mercury when the sun is on the other side. When we're at nighttime, you're not going to see Mercury because Mercury is close to the sun. So Mercury will only be visible just before daylight if it happens to be on that side of the sun. Or just after sunset if it's on the back side of the sun. But the rest of the time you never see it. In fact, most of the time you'll never see Mercury. In fact, and as Tiffany said, if it's just before sunrise or just after sunset, the sky's still really bright. And Mercury is so tiny, you know, it's going to be really, really hard to see. What's that? Okay. Yeah. Just before sunrise or just after sunset. But, no, okay. What I was said before, in late November, which we're going to assume now, is in the early morning sky, which is just before sunrise. That's the answer to the question. You circle that one. Okay, well, I was explaining why it's just then that you can see it. Now, here's the worst. It makes the problem even worse. Okay, if Mercury was on this side of the sun, okay, what we see is the dark side of Mercury, so you don't see it. The only way you'll see it if it's on that side of the sun, so it's sort of like a full Mercury or close to it. That's the only time. But then it's even further away, and so it's hard to see. Okay, there's the bottom line. Mercury is hard to see. Where is Venus visible on a dark sky? Okay, let's just say no. Let's use this one. It's low at dawn near the east-southeastern horizon. Okay? So that would again be just before sunrise. Okay? But here's the difference. Some big differences. Estimate how long each is visible in the dark sky. Okay? Mercury, if it's visible at all, will just be a few minutes. Probably hardly any time you'll see it. Yes.
What about Venus?
I just said Venus. Did y'all get Venus? It's also just before sunrise. Okay? Now,
That sheet of paper you have in your hand.
I'm sorry. Yeah.
That's Birmingham Southern, didn't you?
This came from Birmingham Southern.
I printed that.
You did? This was back in 2006. Were you there? All right. Thank you so much for the question. All right. I can't remember her name.
I can't think of her name either.
She had an unusual name.
Yeah, she was Hungarian or German.
It's something like that. Yeah. Real nice lady, too.
Yeah.
Yeah.
They used to actually bring students in to look at the stars, and she taught them all about all that.
Yeah.
I didn't ever get into it, though, but she did
Yeah.
that.
She was good.
This and that.
The reason we started going to Sanford, because Birmingham Southern was closer and I really liked it there, but then I found out that was back when some financial things were getting kind of tight. They were wanting to charge them. And we didn't have it in our budget, and Sanford was free. We went to Sanford. And we found out they had a little bit bigger planetarium too, so that worked out well too. Okay. In fact, does Birmingham Southern even still have it?
No, they turned it into something else.
That's what I thought. Yeah, I tried to reschedule there and couldn't. So Mercury, when is it visible in a dark sky? Just a few minutes at most. But Venus, just a few hours. Never very long, because guess what? Venus is also between us and the sun. So when the sun goes down, it takes Mercury with it, and after a while, it'll take Venus with it too. So in the middle of the night, you're not going to see either one of them, because the sun's near on the other side of the planet, and it took them both with it. All right, good deal. So what is sort of a nickname for Venus? And it actually has two of them, and neither one of them are accurate. The what?
Earth's sister?
The what?
Earth's sister?
Okay, yeah, and there's some reasons for that, and we'll go over that in the chapter we're going to start today. But we often call it the morning star or the evening star. Okay? Now what's wrong with those names? It's not a star, okay. But that's why it's called the morning star or the evening star, because that's the only time it will be visible. Just before sunrise and just after sunset. Evening star or morning star. Usually the first star you see in the first the brightest thing you'll see out there in the evening, usually it's going to be Venus. Because you won't see a star yet, but you'll see it first, yes.
I have a question.
Yeah.
Now, a while back, like a few years ago, I think it was around the summertime, and every time I would see the moon as the sun begins to set, there's always a star on the right, on the bottom left-hand side of it. Every night throughout the entire season, I always see that star. So what kind of star is it? I mean, what's the star? What's his name?
I don't know the answer to that. I think I remember either hearing or reading about that when it was occurring, and I don't remember which one it was. Does anyone else?
It was just below the moon. Then once the sun starts to set, another one appears, thing on the top or the side of the moon. And that one always rise and set with the moon.
Yeah. I don't know for sure. There's a part of me, was the moon fairly close to a full moon then, or was it any kind? All kinds of moons.
All phases.
I'm just going to make a guess. It might have been Jupiter, just for that time, because they wouldn't vary that much over a short period of time, but a long period of time they get further apart. And the reason I would say Jupiter is if the sun's setting here and they're over here, see, Venus is on the same side as the sun, Jupiter's on the opposite. Okay? So then it would be that way. But I may be wrong on that.
And I've seen Mars.
You have seen Mars? Uh-huh.
So we was outside watching the stars, and I saw Mars.
Uh-huh.
Little dim red, little
Yeah.
moving ever so slightly.
Yeah.
That was
It wasn't a very slow plane. No, I'm just kidding. Okay. All right. All right. Let me see. Say again. Yeah. Say again. Brianna. Okay. Knew whatever was said didn't sound right. Okay. Has anyone else snuck in while I wasn't paying attention, which can easily happen? That finishes up the lab. Any questions on the lab? Okay. If you need more time to work on it, you can have it. Otherwise, turn it in whenever you want to. I'll try to get it graded and out there. If you want to, you can turn it in now. Okay. All right, to take this off the scope here. Okay. Good deal. Thank you. Okay. I feel like I'm going awfully slowly, but I'm glad y'all have good questions. Okay. All right. I find it a little interesting how they organize things. We started with the universe. That's everything. Okay? Now we're narrowing it down to the solar system, which is a really tiny part of the universe. So that's where we live, in the solar system. So that's chapter 15. The core concept here, which if you have the big book or if the page numbers are the same, the core concept on page 378, the solar system is composed of the sun and orbiting planets, dwarf planets, and small solar system bodies. Okay? Now, if you got the book, you won't see this figure on it. And I'm kind of glad you don't see this figure. Because you'll never see the planets line up like that. Ever, ever, ever. They just did this to give you a relative idea, basically, of the size and positions of the planet. That's all this is telling you. The distances aren't right, and certainly lining up isn't right. The relative sizes, they're not far off. Okay? The little one right in here would be Mercury, Venus, Earth, Mars. Now, you see a sprinkling around here. Anyone know what that is?
It's the asteroid belt.
The asteroid belt. Excellent. There it is, right there. Then you get Jupiter. One with the pretty rings is Saturn. And then Uranus and Neptune. Okay? Now, I think in maybe your text, you may find one that has Pluto in it. Pluto is no longer considered a planet. Okay? Say again? Are you sure? Yeah, it's a dwarf planet now.
They're still doing it.
Oh, there's still some people that don't ever want to lose it, you know, but in reality, it doesn't fit. Okay, it really doesn't. Okay, on many scales, it doesn't fit. Okay, now, and we'll talk about some of those coming up. So these are the 8 planets, never lined up this way, ever. So don't ever expect to see that. Okay, the sun is in the center. Now that sun, if that were drawn to scale, the sun would be huge, and even the biggest of the planets would be tiny. So everything would be lost in the sauce because the sun is so enormous. Okay, so the sizes of the sun are not. Sizes of the planet are pretty close. Size of the sun is way too small. Okay, that's first. The sun, the orbiting planets. Now the dwarf planets, we'll talk about those in a little more detail very quickly, but Pluto is one. I think there's 1 or 2 beyond Pluto, and there's a couple that are in asteroid belt. So I think there's a total of 5 now. We'll name those in just a few minutes. Okay? Those are the dwarf planets. Then the smaller solar system bodies. Some of these are the moons around the planets. Earth has 1 moon. It's really hard to see here. Right there it is. Mercury and Venus, no moons. Mars has two really small moons. You can hardly see them here. Jupiter has tons of moons, okay? More than any other planet. Saturn has a lot of planets, of moons. So do Uranus and Neptune. I bet you we don't even know all the moons there because we haven't really gotten that close to them to enumerate them all. Okay? So those are the moons. Then, as someone pointed out, the asteroids are smaller solar system bodies. And then there's one other thing that comes in. Comets. Comets are the last of the smaller solar system bodies. Now, there's lots of other junk out there, too, but those are the ones that we've named. What's that?
Where does the comets come from?
They're just part of the solar system. Most of the comets are outside the planetary circles most of the time. But every now and then they'll come in. Now, these planets, they make them look like sort of circular orbits. None of them are circular. There's one or two that are awfully close to circular, but they're all slightly elliptical orbits. The dwarf planets, like Pluto, is even more elliptical generally. The comets, way elliptical. They'll sometimes way out there, and other times come in fairly close to the sun. That's the only time we see a comet, is when it gets inside the rest of the solar system and we see it as it flies by. Okay? So they live in two belts. We'll talk about those later. Okay? Yes?
How big is the solar system? Because due to the way you're describing it, it's so big that so large and vast, and at the end, at the edge of the solar system, the sun would look like it's any other star.
I think it'd still be bigger than any other star, but I can't say that for sure. If you think back in the last chapter, when we were talking about the distances to the planets, well, actually coming up in this chapter, I think we'll see a diagram that does this, especially when we talk about those two belts I talked about that the asteroids, the comets live in. The closer one is called the Kuiper belt, or Kuiper belt, and the other one is called the Oort cloud. It's not a belt, but a cloud. The Oort cloud sort of defines how big the solar system is, and it's out there. I mean, it's way out there. And maybe in the Oort cloud, the sun, it still will be bigger than a regular old other star, but it's going to be pretty small. Okay. Now, 15.1 is talking about planets, dwarf planets, moons, and other bodies, like I just sort of went through. So let me give you the definitions here. Well, first I'll read these points. The International Astronomical Union, IAU, is the governing authority over naming the celestial bodies, and even naming stuff on the celestial bodies. The IAU defines planets, dwarf planets, and the other smaller solar system bodies. And in 2003, not that long ago, were all of you born then? Probably. Okay, Pluto was redefined as a dwarf planet according to the IAU definition. Now, they don't give these here, but that's when it happened. Up till then, it was defined to be a planet. Now, here's in your text. To be a classical planet, those are the 8 interior planets, an object must be orbiting the sun, there's one, okay, nearly spherical in shape, that's the second, and large enough to clear all matter from its orbital zone. What does that mean? Okay. Basically that means, okay, let me give you dwarf planet next. A dwarf planet is defined as an object that is orbiting the sun, same thing there, sufficiently massive to gravitationally reshape itself into a sphere, so that's close to the same, but has not cleared matter from its orbital zone and is not a satellite. Okay? So that's the difference. That clearing matter from its orbital zone. In other words, it has to be big enough, it's basically bounces everything else, or, it defines itself. and Pluto doesn't. Now, let me give you a few other reasons. Well, wait. I'll wait on some of those and give them to you later. Now, what are the dwarf planets? Okay, now, let me read this first one. Some astronomers had dismissed Pluto as a true planet for years because it has properties that do not fit the other planets. Okay, we'll go over some of those. The old definition of a planet was any large spherical object that orbits the sun, which resulted in 9 planets, because Pluto is pretty spherical. Okay, but then in 2003. So after this, here are the dwarf planets. A new astronomical, in 2003, when this occurred, a new astronomical body was discovered. They named it Eris, E-R-I-S, after the Greek goddess of discord, because it threw everything into discord. So that was named Eris. Eris is round, meaning it's spherical, more massive than Pluto, and it circles the sun. Is it a planet? Well, no, not quite. If so, then the asteroid, remember in the asteroid belt, Ceres might also be defined as a planet, as would perhaps 50 or so large icy bodies believed to be orbiting the sun far beyond Pluto. The idea of 50 or 60 planets in the solar system said, hey, we just can't have that. And what they say here, because Pluto does not clear its orbital zone. In other words, it shares that with other objects there. It was recategorized as a dwarf planet. So today there are 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. 8 planets. Okay? At least 5 dwarf planets that we have identified as that. Pluto being one, Eris, which is actually larger than Pluto, Ceres, which is actually an asteroid, Makemake, okay, that sounds like something from Hawaii, and Haumea, which sounds like something from Hawaii. I don't know where they got those names. And many, many small solar system bodies. Now, I also want to focus on one sentence on this first page that is very important to a slide coming up in the future. Because the slide coming into the future sounds like it contradicts this until you read it properly. The sun has 700 times the mass of all the planets, all their moons, and all the minor members of the solar system put together. The sun is more than 700 times bigger than everything else in the solar system put together. Okay. And when we get there, probably today, but if not Tuesday, we'll see a slide that almost indicates that's not true. But they mean exclusive of the sun, not the sun. Okay. So anyway, the sun dominates everything. Everything. Okay. More than 700 times the mass of everything else put together. Now, the average distance from the Earth to the sun is called 1 astronomical unit. It's about 93 million miles. So rather than saying how many billions and trillions and gazillions of miles, they just say so many astronomical units. Okay? That's 93 million miles. So they say in the book 1.5 times 10 to the 8th kilometers. That would be 150 million kilometers. It's a big distance, but it's nothing on galactic terms, nothing. But in our solar system, it's not very big either, but it's okay. Now, here's what our solar system is made up of. The sun, more than 700 times everything else put together. Huge, massive. 8 planets, okay? And these 8 planets have something on the order of 100 moons. I think at least half of those are around one planet, Jupiter. And we'll talk about why that may be true. About a third of them are around Saturn, the next biggest planet, and most of the others around Neptune and Uranus, and only 3 moons inside the asteroid belt. Thousands of asteroids, millions of icy bodies, whatever they are, some could be comets or other things. So here again, the astronomical unit is the average Earth-Sun distance from Earth to Sun. And here they say 1.5. I thought they just said, yeah, okay, I got it right. 150 million kilometers, which would be 93 million miles. The planet classification, we talk about them in terms of their size, in terms of their density, and in terms of their atmospheres. Okay? Now, basically, kind of size and density we're going to sort of put together. The smallest planets and the densest planets are called terrestrial planets. These are the 4 inner planets inside the asteroid belt. Okay, Mercury, Venus, Earth, and Mars. They're mostly rocky materials, like we have on Earth, metallic nickel and iron in the core. If I were writing that, I would have said iron and nickel, because there's usually more iron than there is nickel. Okay? So those are the 4 inner planets. We call them terrestrial because they're smaller and denser. Okay. Now, the giant planets, and sometimes they're called gas giants, those are the ones outside the asteroid belt: Jupiter, Saturn, Uranus, and Neptune. They're mostly hydrogen, helium, and methane. Now, I find methane to be very interesting that it's there, okay? But then it kind of makes sense the more you think about it. But hydrogen, yeah, the sun's made up mostly of hydrogen. Helium, yeah, the sun's made a lot of helium. Methane, wait, anyone know what methane is? It's a what gas? What kind of gas? Oh, you're absolutely right. Very flammable gas. Well, actually, so is hydrogen. Okay, but methane, why is it flammable?
Natural gas.
It's what?
Natural gas. It's natural gas, isn't it?
Yes, natural gas is methane. It could be propane and some of the others. Methane is CH4, a hydrocarbon. Say again?
Most miners are extremely aware of methane because they work around it.
Okay, say that one more.
Most miners
Yeah.
are very aware of methane and conscious of it because they work around it on the ground.
Right. Methane is, like Jacob said, is a form of natural gas, which is, as you said, very explosive. So miners down there chipping away at rocks that could be making sparks fly. If you have a very flammable gas in the area, boom, you're toast. Okay. So they have methane monitors all over the place to make sure there's not running into a high concentration of natural gas. Okay. Now, where does methane come from? Especially the methane we're talking about here on Earth.
Things that die, decompose.
Okay, decomposition of matter, just like all of your petroleum are hydrocarbons, and methane is the gaseous hydrocarbon, natural gas, like Jacob said. Yes.
Is methane found in feces?
Is it what?
Methane
Yeah.
is found in feces.
Yeah, and what comes out with feces too. Okay. Yeah, it's gas. That kind of gas. Okay. Cattle release a lot of methane, especially feeder lots of cattle. Actually, even termites release a lot of methane. And that's what I'm getting at. Carbon, at least when my earlier years, I always thought carbon meant life. Every cell, every molecule that makes up your body pretty much contains carbon. And methane is CH4. So I thought that came from organic material. Feces, decomposition of living organisms. Well, then tell me something. How did these giant planets get methane on them? Okay? There's no living things there. Never have been. Never will be. Where did the methane come from?
Okay, the building blocks of it from outer space.
Okay, yeah. Remember when we said these planets, the stars initially are fusing hydrogen into helium, but then the next step is fusing helium into carbon. So carbon doesn't have to come from living organisms. Here on the Earth, most of the carbon is associated with living organisms. Everywhere else, it's not. Okay, so that's where the methane is from. Now, Pluto, no longer considered a planet, but a dwarf planet, along with the other four: Eris, Ceres, Makemake, and Haluma, or whatever, however you say it. Halumay, is that how you say it? Okay. Where does that name come from? Do you know?
I think both from Hawaii.
What's that?
I think both from Hawaii.
Okay, they sure sound like it, but I didn't know for sure if that's true. Now, this isn't on the slide set, but I want to take advantage of it here. And now the planets will never line up this way either, but this just shows them, again, relative size. This time the sun is a little closer to the relative size, but Mercury's small, Venus and Earth almost the same size, that's why we call them sister planets. Mars is small, not as small as Mercury, but still small. Ceres is the one dwarf planet that's in the asteroid belt. This picture is being on the inner side of the asteroid belt. Then your gas giants or your giants are Jupiter, Saturn, Uranus, and Neptune. And these sizes are relatively close. Okay? Now, here's Pluto out here. And Pluto does have one moon. Okay? It's not much of a moon, but Pluto is so small. And notice Pluto is so much smaller. I'm almost certain our moon is almost as big as Pluto, because it's almost as big as Mercury. So there's Pluto. There's Haumea. Is that how you said it? Mm-hmm. Okay. There's Makemake, and somewhere way out there is Eris. Okay. Now they do have here the Kuiper belt, and we'll be talking about that later. That's where a lot of our comets come from, the Kuiper belt, or some people call it Keeper belt, but I think it's Kuiper. Okay. So there are your dwarf planets. One in here, Ceres, Pluto out here. Outside of that is Haumea, Makemake, Eris, and there may be others out there. Dwarf planets, not real planets, your major planets. Now here's something that I've heard a lot about in the last few years. I find it really, really, really fascinating. They really do believe there's a ninth planet. It's not Pluto. That's why when someone said, some people say there's still 9 planets, I didn't want to argue with that because some people think it is, but it's not. It's another gas giant. Way out there. Because you'll never see Neptune. You may see pictures of Neptune, you'll never see it. It's so far out there. Even though it's a big gas giant, it's not. It's so dim you'll never see it. So guess what? There could be another one out there somewhere. With telescopes, we can see Neptune. So far, we haven't found that other one. But there seems to be some mass out there, just gravitational field out there, but it's so far away. Yes?
So you remember when you was going over the dwarf planets, right?
Say it again.
You remember when you was going over the dwarf planets a few
Yeah.
minutes ago? I think you left out one.
Which one?
Sedna.
Second?
Sedna.
I don't think I've ever read about that. It's not mentioned in our book. Is that a new one?
Yeah, not that new, but
Well, this one only mentions 5. Ceres, is that the one that you're talking about? Ceres? Okay. Ceres, Pluto, Haumea, Makemake, and Eris.
I guess you could classify that.
Yeah, I don't know.
It's far away too. It's
Yeah,
very-
wait, okay. Yeah. There's lots of people who disagree with some of the things here. But anyway, that's it. Now, the order of the planets, okay? This is what we've been talking about. No, this is the figure. I knew it was coming up somewhere. This lists the 9th planet here Pluto, that ain't a planet anymore. It's a dwarf planet. And it does show that one little moon there too. And I'm almost certain that at least one moon of Saturn and possibly one or more moons of Jupiter are bigger than Mercury. Okay, so we have a whole variety of things going on out here. Now, again, you'll never, ever, ever see them line up this way. Now, one of the things to remember I talked about, we think of these as near circular orbits. They're not. They're elliptical. But Pluto's is so non-circular. It's so very elliptical. There are sometimes when Pluto is actually inside the orbit of Neptune, and most of the time it's way outside. This is its average orbit. There are sometimes it's actually closer to the Sun than Neptune is because it has a highly elliptical orbit. So that's another reason people didn't want to classify it as a planet. And here's yet another one. All 8 of these inner planets, of the real planets, form a fairly narrow band around the Sun. They're almost in the ecliptic of the Sun. I mean, they're slightly off, but not far. Okay? Pluto is like this. I mean, it is way out of line with the other planets. And that's why another reason it was classified a dwarf planet. Okay? All right. Now, here's a question, and we're not going to go into great detail on it. This is 15.1 on page, example 15.1 on page 380. How long would it take to travel the average distance between the Sun and Earth at a typical jet airline speed of 1,000 kilometers per hour? It would be about 600 miles per hour, using the equations from 2.2. We haven't dealt with those equations, so let's just read the answer. Okay? About 2 months of travel. If you could travel at 600 miles per hour for 2 solid months without refueling or anything else, if you could do it, it would take you about 6 months to get from Earth to Sun. Of course, who would want to? You're going to burn up long before you get there. But if you could, that would be it. 15.2 is another sort of crazy question like that. Interplanetary space probes travel about 7.3 kilometers per second. That's a little, let's see. That would be 4 miles a second or so, approximately. Okay? How far could it travel in a year? Well, that's about, why they ask these questions, I don't know. 2.3 times 10 to the 8th kilometers. In other words, that's about 230 million miles. Okay, much faster than airplanes. All right. Now, the next part, the big part of this chapter, is going to be looking at each planet individually. But before we do that, there is one of the best tables I've ever seen put together, but it's so dense you can't read it from where you are, and that's why they did put it on the slide set. But please pay attention to this table when you do get your book. It has several properties of the planets, and again, it lists the 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? And they give average distance of the Sun, first in millions of kilometers, which I don't think in terms of, but astronomical units, I can think in terms of that. In other words, the distance from Earth to Sun is 1 astronomical unit. That's how we define it. So these would be closer than that, so it'd be fractions. These are further than that, so they'll be much bigger numbers. Now here's what I was talking about before. We are fairly close to being in the same plane. So this is the inclination to the ecliptic. Of course, the Earth and Sun, that makes 0. But the others are either slightly above. Mercury is the most out of line, but that's because it's closest to the Sun. Just a little bit of change there is going to be a lot of degrees, 7 degrees. Venus, 3.4 degrees. Mars, 1.9, 1.3 for Jupiter, 2.5 for Saturn, 0.8 for Uranus, and 1.8 for Neptune. Now, if Pluto had been included, anyone want to make a guess what his inclination? Say again?
It's far.
A little louder.
It's far.
Yeah, it's way out. I've read somewhere around 17 degrees. Nobody else is close to that. It's way out of line with the others. Okay? Now, they don't mention it here, but that's it. Okay? Then they say orbital period. Now, that's how long it takes to go around the sun. This is in Earth years. Of course, those closer to the sun go faster, and those further from the sun usually take a lot longer. We'll look at those. Rotation period. This is what a day is. Now, there's some really interesting data here. Mercury spins pretty slowly. It takes 59 days of our days, which is one spin, for it to go around. Okay? Whereas Venus, talk about slow, it takes 243 Earth days, but guess what? It's spinning backwards. Whoa! Now, what could have caused that? They think it had to have been some major collision early in this process and actually got it spinning backwards. Awfully slowly, but still spinning backwards. Earth is about 23 hours. It should be 24, I think, but anyway. Mars is just a little bit longer, so it's very similar to Earth in that. Jupiter, only 9 hours to make a spin, and that's a huge planet. That's really flying. Saturn, 10 hours. Uranus, 17, but it's a minus sign too. Now, Uranus is sort of bizarre. Venus is actually spinning backwards. Uranus, the pole is almost pointing toward the sun and spinning backwards. But it's so far out there, who cares? I mean, no, we didn't say that. Okay. And then Neptune is almost the same as Uranus, but spinning in the right direction, 16 hours. Okay. Now, here's where some things get sort of interesting. What are the relative masses? Now, this is how many Earth masses there are. Mercury is 1/20th. Am I got that right? Yeah. 1/20th the size of the Earth. 0.05 Earth masses. That's tiny. Okay? Really tiny. Venus is almost the same, 0.82. Earth, of course, is 1 Earth mass. Mars, also pretty tiny. Just barely more than 1/10 the mass of the Earth. 0.11. Jupiter? Almost 318 times as massive as the Earth. You could fit 300 plus Earths inside Jupiter and have room left over. Okay? So easily. Okay? Saturn, 95 times bigger than the Earth, more massive than the Earth. Uranus, almost 15 times, and Neptune, a little over 17 times. So when they say they are giants, they are giants out there. Inside, we're pretty small. Okay? Equatorial dimensions. And these are diameters in kilometers, but also in Earth radii. Okay? Where the Earth radius of 1. So the radius of Mercury is just over a third what the radius of Earth. Now its mass is way less, so it's not a very dense planet. Okay? Well, it's sort of dense, but not too much. Okay, Venus, almost exactly the same size as Earth. 0.95, we're 1. So awfully close. That's why we're the sister planets. Okay? It's hard to hold up. Mars, 0.5, so it's about half the diameter or radius of the Earth, a little more than that, whereas Mercury was just over a third. Jupiter, 11 times the diameter of the Earth. Saturn, 9 times. Uranus and Neptune, about 4 times. So, way bigger. Now, here's where things get really interesting, I think. Remember we said the inner 4 planets, what was their classification name? Terrestrial planets, meaning rocky. That that means they're denser. Those others out there are gases. Those are pretty light. These are dense. Look at the densities here. These are all in the same unit, grams per cubic centimeter. Mercury, 5.43. Okay? Venus, 5.25. It's a much bigger planet, but it's not quite as dense. Earth, 5.52. The densest of all the planets. Earth. Okay? Of all the planets. The densest. Okay? Mars is just less than 4. Jupiter, 1.33. Because it's gas. It's not solid rock, okay, like we are. Now, Saturn, to me, is one of the most interesting ones. 0.69. Just a little bit less than 0.7. Now, does anyone know any densities of common materials? Second? Yeah, compared to, water. What is water's density? Do you know? 1 gram per cubic centimeter. Saturn, 0.7 grams per cubic centimeter. That means if you had a big enough pool of water, Saturn would float. Would actually float. It's less dense than water. The entire planet is less dense than water. Amazing. It's the only planet that would do that. Okay? Now, Uranus is about 1.29 and Neptune 1.64. So they're actually, Uranus slightly less than Jupiter's density and Neptune even more. The atmosphere. Now, this was another way we classified planets. Mercury, poor old Mercury, has basically no atmosphere at all. Okay? Venus is largely carbon dioxide. Here again, I say, what? Because I think the carbon dioxide is coming from people breathing, okay, or fuels burning. Not on Venus. It's out there. Nothing's ever lived there that we know of. I don't think I want to meet it if it did. Okay? Then we get to Earth. Mostly nitrogen. A little bit of, about a fifth of it is oxygen. Does anyone know why a fifth of our atmosphere is oxygen? Plants. Because if it weren't for plants, it would be carbon dioxide. But plants are always taking carbon dioxide out of the air and putting oxygen in. Because everything uses oxygen to combust, burn, breathe, whatever. But plants do it the other way. So thank you, plants. Without you, we wouldn't be here. Okay. Now, then you go to Mars. On one side of us, carbon dioxide. On the other side of us, carbon dioxide. Okay? Now, the trouble with Mars, it hasn't got a very thick atmosphere. Venus has a really dense atmosphere of carbon dioxide. Now, if plants weren't here, we'd have more carbon dioxide than oxygen, because we're still primarily nitrogen. We're the only planet that has mentionable nitrogen in it. I don't know why, you know. It's not that essential for life or anything else, but the only one, okay? Then when you get to the gas giants, Jupiter, hydrogen and helium, Saturn, hydrogen and helium, Uranus, hydrogen and helium and methane, and same with Neptune, hydrogen and helium and methane. Now, this next one, I've seen no reason to put it in here. Solar energy received. Well, guess what? The ones closest to receive more, the one furthest away less. So Mercury is 13.4. The units they use here, Venus 3.8, Earth 2.0, Mars 0.86, Jupiter 0.08, Saturn 0.02, Uranus 0.006, and Neptune 0.002. I mean, that's just how close they are to the sun. The ones out there hardly receive any energy at all. All right, that table, when you get your books, that's worth paying attention to. It's really some interesting stuff. Okay? So let's talk about Mercury. Mercury is the innermost planet. There aren't any closer than Mercury. It has a fairly highly elliptical orbit just because it's so close, okay? So it's a fairly highly elliptical orbit. and it's only about 4/10 of the distance between the Earth and the Sun. So let's say the Sun is here on this dividing line, okay? And let's say the Earth is here, right about where that 3 is. Is that okay? Mercury would be about here, 4/10 of the distance between the Sun and the Earth. It's awfully close to the Sun. I mean, it is so close to the Sun. Now, this is repeating some of the things I just talked about. Its orbital period, how long does it take to go around the Sun? Only about 3 months. So it takes us a year to go around. It takes it about 3 months. That's because it's so close, okay? The rotational period, though, its day, is about 2 months. 59 days to spin one time. So therefore, every year on Mercury is 2/3 of a day. I mean, it's really bizarre if you think about this. This is 2 months, that's 3 months.
You said 6 months around the sun?
No, it takes 3 months to go around the Sun.
3 months, okay.
Yeah, it's right here. And 2 months to rotate. So its days are really long compared to its years, which are really short. Okay, and this is what we talked about before. Visible shortly after sunset or before sunrise. If it's ever visible, that's the only time you'll see it. And probably only for a number of minutes. Okay? Because it's either the sun is going to come up and bleach it out, or the sun's going to set and drag it down below the horizon. Okay? Now, these two expressions here relate to each other. There is no measurable atmosphere on Mercury. The only planet with no measurable atmosphere. Which means it's highly cratered. Now, what do we mean by that? Second? It's a lot like the moon because the moon has no atmosphere too. And what makes it highly cratered? All this space junk that hits it. Okay? Does much space junk hit the Earth's surface?
No.
Not much. Every now and then something will. About maybe 6 or 7 years ago, they think maybe an asteroid or something fell out of orbit and hit out in Siberia somewhere.
It never hit the ground.
Say again?
The initial impact never made it to, like, the rock itself, it never made it to the ground, but bits and pieces of it.
Oh, you mean it broke apart?
Yeah, it came in instead of straight down, it came down.
Okay. Now, most stuff that hits the Earth's atmosphere out here burns up before it ever gets to the Earth. Those are called meteors. But when they do hit the Earth's surface, those are called meteorites. We'll talk about that later, too. But guess what? Why do they burn up? Frictions between what? Our atmosphere. So it burns them up. They get so hot, they literally decompose. And that's why they burn up, too. Now, sadly, get their names crossed up. I think it was Columbia, the space shuttle, that when it was coming back in, it caught fire. Was that Columbia or was it Challenger? I can't remember. Okay. Say again? Yeah, Challenger. Okay, Challenger. Okay. I happen to have been, of all places, in Huntsville, Alabama, the day that happened, at a swim meet where my niece was swimming, and suddenly the whole place went, because people just watching their phones and stuff. It was terrible. The heat shields, enough of the tiles broke away on takeoff for some time. And when it came back in, there was nothing to absorb that, and it burned up just like all the other stuff they had.
Is this when the rocket went, when the astronauts went out in
Second?
space? Is it the same day when the astronaut was supposed to go to space when the rocket blew?
Okay, no, that was the other one. One was Columbia and one was Challenger. Now, I can't remember which was which. That one was earlier when, right after takeoff, it blew up. And that was the first to have a female astronaut, wasn't it? Sally Ride? Okay. And she was not a teacher, was she? Or she was a teacher. Okay. Because we sent up some more later, and I couldn't remember which were which. Okay. But that's why Mercury is highly cratered because all this stuff that usually burns up in our atmosphere, no atmosphere to burn it up, it just crashes into the planet. Crashes into the planet, just like it crashes into the moon. It is by far the smallest planet. Okay? Smallest mass and smallest diameter. If Pluto were included, Pluto would be the smallest. Now think of this too. Pluto is more rocky. But the four inner planets are the rocky ones. The four out here are gas giants. It's beyond the gas giant, so it should be a gas giant. It's not. So that's another thing that makes it a dwarf planet, not a real planet. Okay. Now here are some pictures of Mercury. Okay, here's the first one. As the sun is setting or rising, whichever it happens to be, that's the only time you'll see Mercury, because Mercury is revolving around the sun. The brightest it'll be is when it's on the back side of the sun, when we get a full Mercury, because when it's closer to us, we have a crescent Mercury, so tiny it's hard to see. So here we have about a half Mercury, and that's going to be hard to see too. And it's only going to be there for just a few minutes at most. That's either as the sun's going down or the sun coming up. If Mercury was over here, in either case, you'll never see it, okay? Because it's below the horizon. When the sun comes up, it bleeds off, or it would have set before the sun sets, and you'd never see it. So only occasionally you'll see the, I don't think I've ever seen Mercury, but if you studied it well enough, you might see it. Okay? Here is actually a composite photo of Mercury, made of several different photos put together, and you see it's just speckled with craters because nothing is there to block, to keep that space junk from hitting the planet. Okay. The next planet out, Venus. Beautiful name, isn't it? The goddess of beauty, right? Or love, or something like that. You would think it would just be a wonderful place, wouldn't you? You don't want to go there. You don't want to go there. Okay? Okay, again, if this was the sun, and there was the Earth here, it's about 7/10, a little over halfway, but not 3/4 of the way between the sun and the Earth. Not quite twice as far as Mercury, but close to it. Okay? Often called the morning or evening star, because when it's visible is either shortly before sunrise or shortly after sunset, because it's also between us and the sun. So when the sun goes down, it'll be a while, but Venus will go down with it. Okay. Now it also comes in phases. I've never noticed these phases, but if you had a good enough set of binoculars or telescope, you could probably see the phases of Venus just like you see the ones of the moon. Okay. Its rotational motion, this is the strange thing about it, is opposite to the orbital motion. So if it's going around the sun this way, it's spinning the opposite way. So the sun rises in the west and sets in the east. Strange, bizarre, okay? And we said that Mercury was bizarre because its year was 3 months and its day was 2 months. Venus is even worse than that. The Venusian day is longer than the Venusian year. Okay? Looking back at our table there, the Venus spins once every 243 days. That's almost a year on Earth, and yet it spins. Where is it? Orbital period is maybe about 5 months. Okay, so its day is longer than its year. The time it takes to spin once is longer than it takes it to go around the sun by a pretty significant amount. Now, because it is our closest neighboring planet. Our closest neighbor is the moon, of course, but the closest neighboring planet, we've sent a lot of probes out there, okay? And so we've studied it pretty well, mostly carbon dioxide in the atmosphere, and there's a thick, dense atmosphere. What do we call carbon dioxide here on Earth? Say again? A greenhouse gas, which means what? Yeah, it keeps heat from going back out. See, radiation comes in from the sun. Now, our atmosphere blocks the harmful stuff there, only allows a little bit in, but then the carbon dioxide, the methane, other things in our atmosphere traps it in, and we don't emit as much as comes in. So our atmosphere is wonderful for us, but the more carbon dioxide, the hotter it gets. And guess what? Last year was the second, I heard this on the radio, I think yesterday, second hottest year ever recorded. And the hottest year was 2016, I think. So the two hottest years have been in the last 3 years, okay? And then probably the 5 hottest years have all been in the last 5 years.
Is that a good thing or a bad thing?
We don't know for sure, but it doesn't seem good right now.
You probably consider this as a minor joke. It says
What's that?
2016 was the hottest year. Isn't it good that we had the second hottest year? I mean, it's going down.
Well, okay, that trend is okay, but you asked me about January. Have you ever experienced a January that we've been above 70 degrees so many days? We have had hardly anything below freezing. I think next Sunday and Monday night are going to finally get below freezing. But most of our below freezing was back in December. We have only had maybe 1 or 2 days in January. January, our coldest month of the year. So I think we're getting ready to set a hottest, warmest month ever. Now, we could get cold in the last half and change that.
But that means March is going to go crazy. March and April.
Who knows?
I know why. I did some research. I looked at the Storm Prediction Center website. It is a El Nino year, but it's
Yes.
not usual one. It's a neutral El Nino year,
Okay.
which means I have looked at it, but it,
Yeah.
but it causes the above average
Warmer than
temperature
average, yeah.
in January.
But I've never known it to be this warm. I mean, we had some nights in the 60s. Nights in the 60s in January? You're kidding me. Most days don't get in the 60s in January. This is bizarre. Now, like I said, the last half of the month may be way cold, and we may average out, but it doesn't seem like it. Okay. So, here's the point. Venus is mostly carbon dioxide, which is all greenhouse gas, okay? Now, what does that mean? And Venus is really close to the sun. So it is hot and it stays hot. And when I say hot, I mean, here's the surprising thing. Mercury, you know, that is really surprising. Okay. Remember, if this is sun and this is Earth, Mercury's here and Venus is here. Right. Okay? Now, Mercury's so much closer to the sun than Venus. And surely the side of Mercury facing the sun is the hottest place, probably that you can land on. Okay? You don't want to land on it. Okay? But the average temperature of Venus is hotter than Mercury because of that hot, dense, high carbon dioxide atmosphere. Because the backside of Mercury is frigidly cold because there's nothing to trap the heat. So once it turns away, it gets awfully cold. But Venus, it stays hot constantly. Okay? Incredibly hot. So it's high temperature and high pressure because of that really dense atmosphere. Now, what they didn't mention here are some of the other gases that are in Mercury's atmosphere. Maybe sulfur dioxide, which combined with a little bit of moisture gives you sulfuric acid, carbon dioxide, carbonic acid. So it's a very acid atmosphere. You don't want to be there. If that's the planet of love, I want to give it up. No, I'm sorry, I'm just kidding. That's crazy. Now, the surface is mostly flat, but it does have some volcanic mountains on it. Oh, that's all it needs. It's already hot, and then it has volcanoes. Wow, what a good place to be. Okay. You can't read these, I'm sure, from where you sit, but they'll be in your book when you get them. These are some of the spacecraft missions to Venus. Now, I hope most of you know what USSR is, right? Union of Soviet Socialistic Republic, basically Russia. Okay? US, of course, is us. Okay? Not literally. USSR got to go into Venus, so we said, well, we're going to go to Mars. So we outnumbered them there. But they sent a lot of things to Venus. We sent quite a few. So you see, they outdid us there in big time. Now, this only goes to 1989 or so. In your text, it extends longer, and it goes to, Magellan. Does that have Magellan? Yeah, it has Magellan and then Galileo. Okay, both from U.S. They have two later ones. One of these is ESA. What in the world is ESA? European Space Agency. They got together and decided to do that one, and then the U.S. has sent up Messenger more recently. Okay. Now, there are a couple of examples. How many times would a space probe on Venus's surface have gone around the sun if it had been there 30 Earth years? This is just weird to put a question like that. Basically, take 249 or whatever the number of days in. No, I'm sorry. I had the. That is how many times have gone around the sun. So this would be their orbital period. 0.62 compared to our 1. So divide 30 by 0.62 and you get about 48 trips around the sun. Okay? What difference does that make? But that just gives you an idea. Now, 15.4, how many times has Jupiter rotated on its axis in the last 24 hours? Okay? Jupiter rotates at in a 9-hour basis, so in the last 24 hours, it would have gone around between 2 and 3 times, 2.66. What difference does that make? I mean, I guess it gives you some insight, but they just ask bizarre questions just for the purpose of asking. Okay, so there was Venus, the trips to Venus. Here is a picture of the surface of Venus. Now, I think they colored it this way just to show you how hot it is. That, they think, is a huge volcano. And for them to say it's mostly flat but very, this is the very part, okay? And these could be streams of lava coming out of the volcano. It could be hot streams of molten rock. Who knows what it is? But it's a very inhospitable place. You don't want to go there. And it's very acid. You would try. That's probably why we don't have that many probes that have penetrated the atmosphere, because you have to build them out of such tough material because they're going to deteriorate in almost no time.
Did you say the USSR went to Venus?
Yeah, several times now. Have they ever?
What did they discover?
Well, they share it with us. This may be, I don't know if that's a picture that we took or they took, but now here's something, and this is pretty interesting. When it comes to things like science, a lot of these countries that really can't stand each other's guts, scientists work together pretty well. In fact, one of the most impressive collaborations we have on the face of the earth is that of seismic data. We share that. Everyone shares it. If there's an earthquake or anything anywhere, everyone communicates with each other. I mean, almost instantaneously. It's all set up that way. So guess what? A country like North Korea can't test a nuclear weapon without everybody knowing about it, because we all share and will detect that. And if we know it's not an earthquake, they set off a bomb, okay, because that will also do the seismic activity. Another one is tsunamis. All those who are near oceans, They all share the second because the